Okay, class. Trying to make sure I got all the settings right. I think we're in good shape here. So I'm going to continue on with the discussion on how to use the Carrier Hourly Analysis Program known as HAP. We had kind of gone through how to construct spaces and how to select weather and schedules and walls and roofs and all that sort of thing. The systems we have in this model that I emailed you out, we have a system made for each of the zones, north, south, east, west, and core. And I will attach the PowerPoint that I have that just shows a sketch of the building. It's not up to professional architectural standards, but we give you some idea of the layout on this. But once you get these things built, all you do is select one. And again, there is no run button. It's a right click when you want to execute. And all we can do here, well, we can't really do good simulation results with cost. You can do, I think, some simulation, but at this point, we usually do the design loads. And so you click that and you get this screen where you can just click and select the reports that you want to see. And we're just going to do a couple of them here. And you click preview and it runs, hopefully, and you can see your result. Let's see, I got a little plus key, make it a little bigger. There we go. So for this particular zone, we see we have 11,600 square feet. This is, let's see, the west zone. We see the peak cooling load is 17.8 tons. This is the total load. This is, if you take, this is thousands, MBH is thousands of BTUs per hour. If we divide by 12,000 BTUs an hour, we get 18.7 tons. This would be the sensible load. Sensible plus latent equals total. So if you take the total and subtract the sensible, then you get the latent load. And all sorts of different information. I'll let you look down through there on your own. Here we have this would be for sizing the heating coil at 222,200 BTUs per hour. This is the ventilation air. So for this unit, we're saying 996, almost 1,000 cubic feet per minute. And then you get a CFM per square foot, which is 0.09. If we pull down a little bit more, we see the detailed breakdown on the heating and cooling loads, which this is where you can really see the detailed results of your simulation. You can see the component loads at the zone level, which would be the walls and the windows and the roof and skylights and doors and people, infiltration. All that occurs directly into the space. Then further down, we see additional load that's outside of the space, but yet gets put on the unit. Biggest component probably being the ventilation load. Okay. And so anyway, it sums up, you get the totals down here at the bottom, total sensible and total latent load, add those together, and that should be, let's see, we can look at the sensible, 167,597. If we go up, we get 167,597 rounded to 167.6 thousand BTUs an hour. So this sheet, some of these items summarizes this more detailed sheet down below. Okay, that's enough on the design load simulation. Now, what I want to get into with you would be how to do the annual energy simulations. So the first thing to recall is we have to have two weather files. So we've actually been working, those design equipment sizing is run off of this design parameters weather file. The annual energy simulations comes off of the simulation weather file. So be sure that you have both of these selected before you try to do your simulations. So what we need to do is we need to define chiller and cooling tower to go with the air handlers. Now, to make sure this is right, we need to look at systems for a second and see what type of air handlers. So say we have defined this to be chilled water air handling units. So in order to do annual energy simulations, we need to have a chiller and a chiller plant defined. So we're going to go to, let's do a chiller first. We can do this. Well, lo and behold, I already have these defined in here for you. I thought I was going to be defining those, but we can take a look at them since they're already here. So if it wasn't here, you would just click on that top tab that says, to define a chiller, a piece of equipment. And so under the first tab, general, you just give it a name. And then you have to select equipment function. And so a chiller just makes cold water. Heat pumps are reversible systems. Heat pump could produce hot water. Reversible system could provide hot or chill water. So we're just looking at a chiller. So you have to select the equipment function and then the equipment type. And so these are all of the different types of chillers that you can simulate in the carrier program. So this one is set on water-cooled centrifugal, so we can just stay with that. Okay, you put notes down here, but I haven't done that. So that's it on this tab. The templates, I'm not real sure. I've never really dealt with that. So some of this, if you want to import data from a particular chiller from a manufacturer, you can do that here. I've never done that either, so we're not going to spend much time on those. Here's the design inputs. This is where you set your chill water temperature. I think the first time you pull this up, it defaults to 42. So when you do the homework, you'll have to be careful to get this set to 44, which is, I believe, what I asked you to run. So this would be leaving chilled, CHW chilled water, and then temperature. So that's the chill water temperature leaving the chiller. And this is the full load entering condenser water temperature. So we're sizing this for typical cooling tower would be 95 into the tower, 85 out of the tower. So that's what that second number is. The 44 is just the design leaving chill water temperature. So for a centrifugal chiller, these are default values over here on flow rates, gallons per minute per ton. These are default values that are built into the carrier program. This may or may not be the case. I know in some of the last lecture, we were looking at chill water systems that were designed at 2 GPM per ton. So what we're starting to see is the newer concepts are trying to reduce the flow rates, increase the delta T's in order to reduce the energy spend on pumping. We'll talk more about that. But 2.4 is kind of an old time number on chill water flow. That's gallons per minute per ton of capacity on a centrifugal chiller. And the 3 is on the condenser, GPM per ton. So those are kind of standard numbers. So when these things provide those standard numbers, that's fine. You can go ahead and use those. Capacity, we can let it auto size. That's fine. If you uncheck the box, you have to tell it the tonnage of the machine. This way, it kind of just calculates the maximum tonnage and tells you that, and then you would most likely select a slightly larger chiller just to be conservative. Controls and features, the minimum entering chill water set point is set at 60. That really comes from the chiller manufacturer. If you get too cold of condenser water, you can have oil migration problems in chillers. And so, you would really want to go back to the chiller manufacturer, but we're not worrying about that. So it's okay to just accept these. And the 20% minimum load is fine. And there are such things as heat recovery chillers that have extra 2 bundles on them to recover additional thermal energy to, say, preheat hot water or something to be used. But we're not doing that yet. Input power, this is where you give it the full load kW per ton. It defaults to 0.6, so we'll just use that. Average operating loss, I've not put that in there, so don't worry about that one. Okay, so then under performance, this is the performance map that defaults, and unless you have detailed chiller data, I would suggest that you just accept this. So, there's really not much involved here in defining this centrifugal chiller. So we'll just say that's already there, so I don't need to save it. You'll need to save it. Okay, so that's the chiller. We'll need a cooling tower as well. So there we go. So I've named it. I just called it the centrifugal cooling tower. Modeling method. There's different options here, but we're doing a cooling tower, so this should be checked. Such thing as a dry cooler, GO well, or surface water. It's possible just to take water, say, from a lake and use it in a centrifugal chiller. So anyway, but we're not doing that. Cooling tower model. So this is the design. Wet bulb temperature 78 is a pretty standard number. The range, which is how much the difference between the entering water temperature and the leaving water temperature, we're saying is 10 degrees. And the approach is how cold the water approaches the wet bulb. This is the theoretical minimum temperature that you could get. And so this tower is sized for a 7-degree approach. So 78 plus 7 is 85, and that's our coldest. That's our design leaving water temperature. And full load fan KW, this is a default for this centrifugal tower, which I didn't change. So it's 0.05 kW per ton of capacity. That's a way to define the tower fan energy. Water flow rate, 3 GPM per ton. That's what we put in the chiller as well, so that needs to be coordinated. And here's the type of fan control. So we can do cycling, we could do water bypass, we could do a 2-speed fan, or we could do variable speed. So I've asked you to simulate a variable speed as an energy efficiency option in your homework. So your base model would have the fan cycling, and then you could run the program again, having changed the cooling tower to a variable speed fan in order to get the results from that, and then you have to physically subtract reports from the two. So we'll say okay to that. And so we're good. Okay, so we've defined a chiller and a cooling tower. Now we need to define the chill water plant. And so you can see I have a chiller, a centrifugal chiller plant already defined, but we'll take a look at it. Under the general tab, you just give it a name, which we have, and you can pull this down. And this shows all the different types of plants that you can define. And we'll talk more about this, but we're doing a chiller plant here, so this would be the obvious selection. And that's good. So then we want to go on to systems. Well, these are the air handling systems from the building or complex or whatever that you want to be served by this chiller. So we simply click on these and click add, and you see I already have all of my systems. So this chiller is going to provide the air conditioning or the chill water to air condition the entire building. Okay, so that's pretty simple. Service hot water. This is for like domestic hot water and stuff. We're not worried about hand washing water heaters and stuff right now. So we're going to skip this tab. It's grayed out anyway. Okay, so excuse me, getting a little bit late. So this would be the plant configuration. So under equipment, I could specify size, or I'm just going to let the program auto size things. It wants to know how many chillers that I want to use to satisfy this load. And I just want one, and it's to be able to handle the entire capacity. And I didn't put any oversizing in. I mean, you could put 5 or 10% in there if you wanted to. It's just going to make the chiller that much bigger in the printouts. You could not do that and then add it later by hand if you wanted to in terms of capacity. If you under cooling controls, equal loading would be if you had multiple chillers, how were you going to share the load between them? But it really doesn't matter with just one chiller. Leaving chill water temperature control, you have some different control options here. We could reset that with outside air, or we could reset by load in order to maintain a constant return water temperature. So those are some other options. Maybe we'll look into those later, but right now you can just do constant. And there's our design, leaving chill water temperature of 44. We're not doing free cooling. Those are the options and stuff. And the cooling tower configuration is right now we'll have this one tower for each water cooled chiller. So we have one chiller, one tower. Trying to keep it simple. Schedule of equipment. Let's see what we get here. So this is where you tell it, in your chiller definition, we've got 2 chillers. So you see if I click on this pull down, I can select either chiller for this plant, or I could now create a new chiller for this plant. But so this plant was to be for the centrifugal chiller. Full load capacity, it's going to be auto sized. Flow rate 2.4 GPM per ton on the evaporator and 3 GPM per ton on the condenser. And then this is the cooling tower. So again, I only have one in there. I could create a new cooling tower here, but that's why I created this one. And so the tower flow rate is consistent with the chiller, 3 GPM per ton. All the rest of this stuff is grayed out, so we don't really need it. I think this is if you have multiple chillers or something. I'm not sure, but anyway, it's grayed out, so we don't need to put it in. This shows us right now the estimated maximum load is 253 tons. That's good. Distribution, we have to go here. I've given you some information on the pressure drops for the chill water pump and the condenser water pump, so you'll need to Look at some of this on the chill water distribution pump. It's constant speed. It could be variable speed, or it could be a primary secondary with a variable speed secondary. So there's different options, but we're again going to keep it simple. The coil design delta T we're going to say is 10. These are default numbers. I just left it here. And you want to set this pump performance unit on feet of water gauge. So that's the feet of head that is created by the pump. And so then we come down here, and so this is the first and only chill water pump that we're going to have in here. The flow rate is 2.4 gallons per minute per ton, and the feet of head is 70, mechanical efficiency is 70, and the electric motor efficiency is 94. Fluid properties, we're just doing fresh water, standard density, and standard specific heat. Then we go over here to the condenser. Again, we don't have too much. Um, let's see, we have the control, pump control, and let's see, pump performance. Water. Okay. I was thinking we had to put in the pump head in here, but not giving us an option. So I guess that's okay the way it is. So we'll say okay to that. Okay. So we have a plant built, and now we need to go to a building. Okay. So we just have one in here. It's called the base case building. So I'll double click on that. Or if you wanted to build one, a new one, you just click new default. It will come up with this, and you start filling in the information for the tabs. Looks like we have also defined a hot water system. Don't I'm not sure. Well, I guess we do need to do that because we got heating coils in this thing. So we'll go back and look at that definition here in a second. I skipped over that, but you just give the building a case. Whatever plants you have defined in the model, you can select. I mean, you could have different chiller plants, and then you would figure out which one you want to put in this version of the building. So I only have two. I have a chiller plant and a hot water system. So they're both in this building. There's again my systems. I can select which of my HVAC systems that are in this building that I am defining, all of them in this case. Miscellaneous energy is energy that you want to show up in the electric cost or the gas or the operational cost of the building that is not defined in the model thus far. A good example would be parking lot lights or any energy use. Maybe you've got a big extension cord that you've run to an air compressor that sits out behind the building and you want to put that in. Well, you would have to define it here. You would check uh, this box, and then you would select the energy type, the peak use, and give a schedule to define it. So we haven't done that in this model. And the last would be where we select our utility rates. Let's see, we don't have an electric rate in here. Well, we're going to have an electric rate. Whoops, we don't have an electric rate in this folder. I guess, well, we better have an electric rate. So I'm just going to do change the name a little bit. Test electric rate. Simple. We'll just make it easy. Let's say it's 10 cents a kilowatt hour. We'll put a tax rate of 5% on it. It's not 60. That's all you got to do for a simple rate. You're going to get to do a more complex one, but I don't want to do that right now. Okay, so we have a building defined. So how do you run the building? Oh, I know, we need to go back to plants. Yeah, I didn't look at this hot water system. Okay, so again, give it a name, define the type of plant. So we've got a hot water plant, a hot water boiler. It's serving these systems. This is domestic water, I believe. So we're not going to do that. On this hot water plant, again, we have boiler and heat pumps. We just have one boiler. It serves 100% load. You don't have to mess with this because, see, this is if you have multiple boilers. So the only thing, in fact, it doesn't give you an option because you only have one boiler. So it's equal loading. That's hot water system temperature control, I believe. It's a hot water control. It's constant. We're trying to make it simple. We're setting it at 180, and we don't have any auxiliary heating. Schedule of equipment. This is where you have to have or define a hot water boiler. We'll look at that here in just a second. Gives an estimated maximum load based on what it sees at that point. Distribution. We have a constant speed pump. We could have variable speed, or we could have a primary, secondary, but we're going to keep it simple over here. Coil design delta temperature drop 20. No, we're not doing any heat losses right now. And yeah, here's the hot water pump. It's size for 50 feet of head, 75% efficiency, and the motor is 94%. Fresh water, and those are the water specs. Okay, I took care of that. Now let's see. We had a boiler defined down there, which we haven't looked at. So we got to do this. Hot water boiler, not much. Given a name, natural gas. As a fuel, it could be hot water or steam. We're just going to make hot water. We're going to auto size the design hot water system. Temperature is 180. Hot water flow rate. Hot water flow rate 20. I think that has to be GPM. Looks like that was defined incorrectly. If it's going to be a flow rate, it's got to be, it can't be degrees F, it's got to be GPM. It may have been a mistake in my model. Overall boiler efficiency, I expect it just kind of swagged at 80%. And this would be for like a blower, some external electrical load. This does the efficiency change as a function of load on the boiler? If you had good information on that, you could put it in. I've just kind of made this up, so I'm not going to worry about it. So I'm just going to say okay to this. So that's everything. So to run this thing, you bring up the building and you select it, and then you right click and print view simulation results. And this is, it's got a lot of reports. You should run, look at most of them. You can only get billing details on one energy source. I think that's actually kind of a weakness here, but you have to pick what you want. So right now this is set on electric. And oh gosh, you can get more detailed user profiles for given dates. I don't usually mess with this part, so I'm not super familiar with that. But if you click preview, then it'll run, hopefully. And it takes a few minutes to run through a model of this size. We've got 5 different big spaces and 5 different air handling units and the boilers and the chillers and all that stuff. But Anyway, we made it. I'm getting on this base case about 230,000 a year. You can see the breakdown, fans, cooling, heating, pumps, heat rejection fans. That would be cooling tower. We've got lights, almost 100,000 a year. Miscellaneous other electric equipment. That would be computers and equipment in the spaces, that sort of thing. And so you can look down. If you check a lot of those boxes, you just get all kinds of reports. Some of them, you get some pie charts that are actually fairly pretty. We get down here a little bit. And this is a Word, I think it's a .rif, which is a Word format. So this can be saved and opened in Word. You can cut and paste out of here, do whatever you want to. But there's really a lot of good information. You know, you have to dig a little bit, get a little bit used to looking at it. But you can use this to put together a very nice report. I'm trying to skip through here a little bit. There's later on we get down to monthly type information someplace down here. Yeah, this is getting into monthly type stuff. You get the bar charts to show you how all that goes, just to help you evaluate, what kind of job you've done. Someplace getting down. Yeah, you get the big landscape detailing energy use by category. So there's a lot of good information there. So I'm going to close that out. So basically what you'll need to do on your homework is run your base model, save it away, then run your options one at a time, save those reports away, and then get into those reports and pull out the information to compare and contrast and calculate savings or differences in energy costs based on whatever potential projects you have simulated. Okay, team, I'm not sure how long that is, but that's probably long enough. It's as long as I want to do tonight and probably more than you want to listen to. So give this a listen. I hope it helps you with your homework, because this is a really powerful tool, and we need to make sure that you guys become fairly comfortable with using it. So I'll send you an email with this shortly, and I may send you something else, but if not, I will see you next Tuesday. So hope you guys have a great night. Bye.